Hello everyone, and welcome to the third and final demonstration video for the NIMS Step Block in Machining 220. In the last video, we finished all of the planar surfaces and features, and so today the only thing remaining for us to do is put some holes in this thing. The first hole that we're going to attempt is this one right here that we pre-drilled during the roughing stages. But before we go ahead and machine anything, let's talk a little strategy. Okay, so the position of this 750 thousandths of an inch diameter hole is 500 thousandths from datum D, the front of the part, and 2 inches from datum C, the left side of the part. We already pre-drilled this, but remember that we added about 15 thousandths of an inch to both of these dimensions because we knew that we were going to take some material off of these surfaces, and so the position of the hole was going to change. The position of the pre-drilled hole is going to be relatively close to this position, but it's not going to be exactly on position. And it's very unlikely that it's going to meet the requirements for this tolerance of position control. So position within 8 thousandths of an inch relative to datums A, C, and D. Now I talk more about this particular tolerance and how to inspect it, what it really means, in another video. But suffice it to say, we've got to get the position of this hole pretty close. So one way to enlarge this hole would simply be to get a 3/4 of an inch drill and run that through the existing drilled hole. That would get us pretty close to 750 thousandths. Whether it would get it within plus or minus 5 thousandths of an inch is maybe another story. And the surface finish would probably be pretty junky. So one step better would be to put a 3/4 of an inch reamer through that hole. And that would certainly get us on size and give us a really nice finish. The problem is that both of these aforementioned methods of enlarging this hole are not going to adjust the center position of the hole. A drill or a reamer will simply follow the existing hole. That might get us the correct size for the hole, but it won't get us on position. In order to change the position of the hole, we need to use a tool which is capable of producing a very accurate hole with a good finish and is capable of positioning that hole wherever we tell it to. And that's the offset boring head. This tool is mounted with an R8 taper, like all of the tools that we mount in the Bridgeport. On the end of the boring head body, there's this sliding boring bar holder. It's mounted in a dovetail, and there's a little screw right here that can actually move this whole block right here in and out. There are a bunch of 1/2 inch holes here in various different orientations and some set screws, and those are for holding boring bars. We have these sets here of indexable carbide boring bars designed for this style of boring head. They've got a 1/2 inch shank, little triangular inserts, and those just fit in here like so. So the way that this works is very simple, right? You just lock down the set screw, right? And now you have a cutting edge which rotates with the spindle. And so as it's spinning, it's inscribing a circle, and that is going to be the diameter of the hole that you cut. So this gets fed through the hole like this as it's spinning, right? And so this is basically the milling machine equivalent of using a boring bar in a lathe. The way that you actually adjust the diameter of the hole that you're cutting is using this little lead screw right here, okay? So this is graduated in thousandths of an inch on the diameter from 0 to 50, so 50 thousandths of an inch total. You just use a little Allen wrench to actually rotate it, right? And you can see that as I spin it, the entire head, or this boring bar holder here, slides on the dovetail ways, and you can move the tool in and out. Pretty straightforward, just like adjusting the cross slide on the lathe when you're adjusting the diameter of a hole that you're boring on the lathe with a boring bar. As you can see, there are a number of different lengths of boring bar here, basically for getting into various depths of holes or holes that are deep inside of some material. But really, you want to go with the shortest boring bar that you absolutely can, because the more boring bar you have sticking out, the more you're going to run into deflection and chatter. Again, just like adjusting a boring bar on a lathe. This type of tool is inherently not rigid, and so we really want to have a minimum stick out past the end of the offset boring head here. Another issue with this tool is that it is inherently unbalanced, right? Because it's not symmetrical about its center line, right? This sliding boring bar holder here can actually move around in different positions, and the boring bar is also going to shift along with this holder in order to cut different diameters. And obviously, the bigger the hole that you're cutting, the more offset the holder is going to be, and so the more unbalanced it's going to be. Whenever you rotate an unbalanced mass, it leads to vibration and therefore to chatter and dimensional inaccuracy. So we want to maximize the rigidity that we can achieve here, and we're going to need to dial in the feeds and speeds and depth of cut because it's very, very sensitive to those parameters. That's why I always recommend, in fact, it's a very, very strong recommendation, almost a requirement, that you take a few practice cuts with this offset boring head on some scrap material before you go in to try and machine your actual part. That way you can work out all the kinks before you go ruining your part that you spent so much time and effort finishing to this point. So something like this, just a piece of rectangular bar that you can pre-drill a bunch of holes into and mess around with. Obviously, you should use the same 1018 mild steel that we're making the part out of so that you can test the cutter under the same conditions as on your final part. There are a couple of different resources available to you for more information on offset boring heads, how they work, what the names of the different parts are, how you adjust them, and the data for feeds and speeds. Okay? And so the first one is actually this handout that comes directly from the manufacturer of the offset boring head that we use, which is Criterion, okay? And the other is the operations manual, okay, which has a very, very detailed and extremely useful section on using an offset boring head. And one of the very important things that it mentions is down here in the very bottom left-hand corner of page 8-16. This chart is showing us the effects of various different orientations of the boring bar inside of the offset boring head. Basically, the boring bar can be adjusted anywhere in 360 degrees of rotation inside of the hole on the boring bar head. And that will change the orientation of this cutting edge right here on the tip of the insert to the inside diameter of the hole that we're trying to cut. What we want is for the cutting edge to be right on the center line of the hole. That way the cutting edge geometries that are built into the tool will be properly oriented relative to the surface that's being cut in order to cut efficiently and effectively. If the cutting edge is too far past the center, then actually we're going to be rubbing behind the cutting edge and we won't be able to cut at all. We'll just be smushing material around. If the cutting edge is too far below the center of the hole, then we will have changed the back rake angle on the top of the tool here relative to the surface that's being cut so that this tool will not cut freely. Basically, it's like we took out the back rake angle. So now the top of the tool at the cutting edge is like 90 degrees relative to the surface that's being cut. Rake angles on tools help us cut more freely. They reduce the amount of force required to actually cut, and so that makes the cut much more effective. Without a rake angle, we're going to get deflection and poor surface finishes. So it really is important that the cutting edge is on center. This is usually something you can just adjust by eye. So looking down the length of the tool, this is the cutting edge, and so based off of its placement, the cutting tool is going to have to rotate this way. Okay? So, in this position, it's too far below center, and in this position, it's too far above center. But if we rotate it just right, we can get that cutting edge so that it's aligned to the boring head. And so you can even take like a ruler or something and kind of just step out the center of this hole that's adjacent to it, and then you can see that the cutting edge lines up very nicely with that. I will say that adjusting the rotational position of the boring bar and the boring head is one of the parameters that you may have to adjust in order to get this thing to cut well. But that's something that you're going to have to evaluate at the machine. Okay, let's set the part up in the vise to cut that hole. As in the past, we're going to put the part down on parallels. But remember that this hole is so close to this sidewall right here that we have to really think about the thickness of the parallels that we're going to use. So far, we've been using parallels that are 1/8 of an inch thick. And right now, the distance from the inside of the hole to this surface is right around 1/8 of an inch, just slightly over 1/8 of an inch. So we could get away with 1/8 of an inch parallels up until this point. But as we start taking material off of the inside of this hole, we're going to start running out of room, and then we're going to start boring into our parallels when we bust out through the back side of this hole and start cutting on the bottom. So now we're going to use these 1/32 of an inch thick parallels. These will definitely give us enough clearance so that we don't actually machine into the parallels when we come out through the back side of the hole. So that's what we have these for. I'm going to use these parallels. These are 1 1/16 tall. It's not that important, just as long as you have access to the material that you need to cut, but you still have enough material being clamped in the vise. Okay, everything's nice and clean, parallels included. All right, part goes down. Like so. Make sure that the parallels are pushed up against the vise jaws. Okay, good vise pressure. Okay, seat it with a hammer. Okay, good. Okay, drill chuck goes in, and then the edge finder. Okay, let's position the part a little bit closer. Okay, so we're going to find the position of the hole from here and from here. This is going to be just like we did when we were originally finding the position of the hole to pre-drill it, okay? But now we're just going to go based off of what the print says, which is 2 inches from this surface and 1/2 of an inch from this surface. Okay, turn it on. Bring it part way down. Here we go. Slowly feed in, and right there. Okay, go ahead and zero out the X. Bring up the edge finder. Move over 100 thousandths on the digital readout to account for the diameter of the edge finder. And re-zero the digital readout. Okay, great. Let's do the other side now. All right, we're going to come in with the edge finder. Nice and slow till we just touch off. Right there. Now zero out the Y. Lift the edge finder back off the surface. Move over 100 thousandths on the Y axis on the digital readout. Right there. And zero that out as well. So now if I go to my 0, 0 position on the digital readout, right, I should be right smack dab over that corner right there, and it looks like I am. Okay, so let's go 2 inches in the X direction. Right there. And let's go 500 thousandths in the Y direction. right there. So that should be center of the hole, approximately, right? That hole is shifted position a little bit. And I'm going to go ahead and zero out those positions, okay? And so now I'm going to bore this hole out at 0, 0 on X and Y on my digital readout. That way it's easy if I navigate away from this position, it'll be easy to find it again. And that is, in fact, what I'm going to do here because I've got to put the boring head in. Edge finder comes out, drill chuck comes out, offset boring head goes in. Now before I travel back to the position of my hole and take a cut, let's talk about power feed, okay? Because we're not going to be feeding this with the quill by hand. That's not going to get us a good, continuous, smooth surface. We're going to be using the built-in power feed on the Bridgeport milling machine, okay? And so that requires that we make a few machine settings. Now, way back in the day when we were talking about milling machines for the first time for the angle plate project, I mentioned a few knobs and levers that at that time I just wanted you to sort of forget about, okay? But now we're going to revisit them because all of those have to do with the power quill feed. The first knob is this knob right here, which is the quill feed engage and disengage, all right? So in this position, it's in the disengaged position, and then over here, so you have to pull this little plunger out and then rotate it. There we go. Sometimes you have to rotate the spindle to be able to get it to engage, okay, because it engages a gear, all right? In this position, it's engaged. So now if we turn the spindle on, we can engage the power quill feed. But it should be noted, and it actually says it right here, make sure that the motor is off, meaning the spindle is off when you engage this, all right? You don't want to grind those gears out. Unless we explicitly want to use the power quill feed, we leave this in the disengaged position, just so that it won't accidentally engage, thereby changing the position of the cutter that we have in the quill. The next knob is this feed rate adjustment knob, okay? We actually get 3 options for feed rate, and it's in inches per revolution, okay? So it's actually geared to the spindle, so it feeds a certain number of inches or fractions of an inch every revolution of the spindle, okay? We get 6 thousandths per revolution over here, 3 thousandths per revolution here, and the slowest is 1.5 thousandths per revolution right there. Again, you pull the plunger out and you move it to the feed rate that you want. Sometimes you have to rotate the quill, or the spindle rather, in order to get it to line up so that you can actually put the plunger into the detent. And then we have this lever right here, which is actually how we engage the power feed. There's supposed to be a little knurled knob right here that you can pull out and push in, which actually changes the direction of the feed, but on this mill, it has been forcibly removed by somebody's careless hammer blows. This is actually something that happens surprisingly frequently. People are too lazy to move the table far enough away from the milling machine head when they're setting their part down on the parallels with the hammer, and their hammer blows end up striking pieces of the milling machine head, and this little knob here is a very frequent victim. Okay, if I turn the spindle on, now you can see that this is spinning, and if I pull back on this, it will engage the power feed, and then you can see the boring head actually feeding down. So imagine that this is feeding down through our hole, okay? So that's pretty self-explanatory. Okay, I'm back at 0, 0 on the digital readout, so I'm positioned where the center of the hole is supposed to be. And I'm going to set the boring head to take a skim cut on that hole right now. You can see that right now the cutting edge of the boring bar is positioned just a little bit inside of the hole, which is good. Now I'm going to use an Allen wrench on the dial here on the back of the boring bar, or a boring head, to just move the cutting edge out a little bit until it looks like it's real close to that surface. Okay? Then I'm going to pull it out so that I'm not actually dragging on that inside surface, and I'm going to go another, let's say, somewhere between 10 and 20 thousandths, just what I think is going to take a minimum cleanup cut. there's a little set screw right here that you can use to lock the position of the sliding boring bar holder in the boring head. I usually don't lock it, but I do snug it up just a little bit, just so that it gives us a little bit of, I guess, drag when we're making our adjustments on the dial, and so that this doesn't change position when I'm actually boring, when I actually spin this thing up. Now, I've already optimized the feeds and speeds and depth of cut for this particular operation, but I'm not going to tell you what my settings are. Experimenting with a new cutting operation in order to dial in the desired results is something that a machinist is expected to do on a regular basis, and I really think that you need to start getting some experience with this process. Before I take a cut, though, I want to mention one thing, which is that when we engage the quill feed, we're going to be doing it, manually, by hand, by pulling on the lever. And then we could simply disengage the quill feed when we've reached the bottom of the hole. That's a perfectly legitimate way to do it, as long as you've got good timing and you've got plenty of clearance. But there's something you might want to watch out for. This boring bar is relatively short. And so right about the time that you actually poke through the backside of the hole, meaning that you actually machined all the way through that hole, you're very close to slamming into the top of the part with the boring head. You can destroy your part really quickly if you don't factor in this particular clearance issue. There's a way to disengage the quill feed and stop the boring bar in the correct position, which is safer and more controllable than just manually disconnecting it. And that's setting a stop, okay? So if we position the boring bar in the correct location where we want it to stop, and then we run this physical stop up until it touches this piece right here that actually moves up and down with the quill, then when this bottoms out on the stop, the quill feed will automatically disengage. So let me show you. I'm going to go ahead and turn this on, okay? And then engage the cut, and you'll see it's feeding down, 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 getting closer and closer and closer to the stop. And then when it actually reaches the stop, boom, it disengages. Okay, and so we're still well enough away from that surface where we're not worried about slamming into it. But we also machined all the way through our hole, so this is really an ideal setup. You could, of course, give yourself some more clearance by sticking the boring bar out a little bit further or selecting a longer boring bar. But of course, remember that this is going to start potentially causing chatter issues when you have that much stick out, okay? So it's actually better to leave this nice and short. Okay, let's go ahead and take a cut. Okay, engage the quill feed. All right. Okay, I'm going to retract the boring head, but I don't want to drag the tool across that surface that I just created, okay? And so what I'm going to do is just move the table over a little bit, right? And then I can pull this out without damaging the surface. But I have to remember to move the table back to my 0, 0 position before I take another cut. Otherwise, I will have shifted the center position of my hole by exactly the amount that I just moved the table to retract the tool. I've seen many people make this mistake, so, don't make it. Okay, so it looks like the hole did not clean up all the way around. It looks like there's a nice surface right here that came from the boring bar, but then over here, it still looks like that drilled surface. It's pretty rough. There are two likely reasons why the hole would clean up in one area but not in another. One possibility is that the hole itself is not round, and so it's not cleaning up everywhere. The other possibility, which is more likely, I think, is that the position of the existing hole is not at the position of the new hole that we're cutting right now. The boring bar is only cutting the part of the hole that it can actually reach, but we're not taking a big enough cut yet to cut all the way around. So I'm going to go another, let's say, 10 thousandths, and then take another cut. Okay, same thing as before. I'm going to move the table out of the way. Okay, so it looks like I'm still cutting over here, and I've almost cleaned up on this other side, but not quite. So I'm going to adjust this for another 10 thousandths and take another cut. Now this time, I think I'm really going to be cutting all the way around, so I'm going to introduce a little bit of coolant. I found that coolant actually helps this cut a little bit. Okay, move the table out of the way, retract the tool, get those nasty chips out of the way. Yeah, and that looks really, really good. Let me go ahead and move this out of the way. So I'm going to go ahead and take a measurement on this now and figure out how far we need to go. I'm going to use a telescoping gauge to do this. Okay, set it at a diagonal and then lock it and rock it through the high point like that. Okay, and then we're going to measure over top of it with a micrometer. Okay, right there. So that says 725 plus 1, so 726 thousandths. Okay, so the final size of the hole is 750 thousandths, and we are at 726 right now, so we need to take about 24 thousandths. I've been having pretty good luck with a 10 thousandths depth of cut, so I think I'm going to take this in 2 cuts of 12. Remember that tungsten carbide inserts really don't like to take too small of a cut. So if you try to creep up on your final dimension with increments which are too small, then you're going to get a really poor finish. Okay, so my dial just happens to be at 0 right now. I'm going to give it another, let's see, that's 10, and then 2 more, based off of that little chisel mark right there. Okay, let's take a cut. I'm going to take a final measurement just to make sure that I'm in that ballpark. Okay, and it's telling me 725 plus 13, so 738 thousandths. So 750 is the target minus 738. Okay, so 12 thousandths. That's what we're supposed to be at, right? Okay, so I'm going to go ahead and take that now. Okay, so I'm going to go another 12 thousandths from where I am right now. So that's 10 plus another 2 thousandths on the dial. Right there. Let's take the cut. Okay, here we go. Okay. Final measurement says 749.5 thousandths. So definitely within tolerance. All right, great. Time to remove the boring bar, or boring head. Okay, we can't forget about the countersinks on the 2 sides of this hole. And what makes this a little bit complicated is that it's actually not specified as the countersink, but rather as a chamfer. So here it says 2 times 30 thousandths by 45 chamfer on both sides. What this means is that the single-sided width or the depth of the countersink is 30 thousandths of an inch, and it's 45 degrees off of the side. The tool that we're going to use to make this is a 7/8 of an inch diameter by 90-degree high-speed steel countersink. The included angle is 90 degrees, which means that it's 45 degrees from center, which is how the countersink or chamfer on this hole is called out on the print. In order to deal with chatter and deflection and reduce the stick out, I'm going to hold this in an R8 collet, like so. Okay, collet goes in, followed by the countersink. All right. Now I'm going to move back to the position of that hole. Now I'm going to position this pretty close, just with the quill, okay? But then I'm going to lock it down. I'm not going to be getting my 30 thousandths of an inch depth by going off of the quill, even though there's a digital readout on there, because it's really not as precise and controllable as using the knee. So let me go ahead and turn this on. Then I'm going to slowly lift the knee until I just kiss that edge with the countersink. Okay, there we go. So I'm going to set the dial on the knee crank to 0. Give this a little bit of tap magic. And then let's raise the knee another 30 thousandths. Right there. There we go. Looking pretty good. All right, folks, we're getting really, really close now. We only have 3 more holes to make. 2 little 1/8 diameter pinholes and the threaded hole. So let's just talk about strategy there for a second. So first off, these 1/8 diameter pinholes says diameter 125 plus or minus 1 thousandths. Now, that may seem like a very close tolerance, plus or minus 1, so 2 thousandths of an inch total, but actually that's not that difficult to get with a diameter of this size if you use a reamer, which is what we're going to do. Depth of 500 thousandths, which is 2 decimal places, so plus or minus 15 thousandths, also not terribly difficult to achieve. The tolerance of position control, 8 thousandths of an inch relative to datums A, C, and D. I go a lot more in depth into what these GD&T controls mean in the video in which I discuss the inspection of this part. But just as a general overview here, C and D are of course the front of the part and the left side of the part, and of course those are the datums from which the positions of all of these holes are called out. Datum A is the bottom of the part, and that is controlling the perpendicularity of all of these holes. The M in the circle, the maximum material condition modifier, is something which I think is best left for that other video on inspection. Suffice it to say, this 8 thousandths of an inch positional tolerance is really not that difficult to achieve. But this perpendicularity tolerance within 1 thousandths of an inch to datum A, that is a little bit tricky to achieve, and it's the reason why a lot of these parts get sent back, meaning that they don't pass inspection. Again, I go a lot more in depth into how to interpret this call-out in that inspection video, but basically we need the center axis of these holes to be perpendicular to datum A, the bottom of the part, within 1 thousandths of an inch. Through some careful thought and experimentation over the years, we've developed a strategy for machining this feature which results in a good part most of the time. Let's say 95% of the time. So the first thing is to make sure that the head of the milling machine is very, very tram. Then we make sure that the part is square to the machine with good parallels and shims, as I'll show you in a moment. And as for tooling, we bring out the big guns. We're no longer using the general purpose drill chucks in the cabinet, okay? They're just not precise enough for what we're trying to do here. They have way too much run out, okay? But these drill chucks, made by the Albrecht company from Germany, the combination of this good quality drill chuck, pre-spotting the hole and using a stub length drill is going to help us achieve that perpendicularity control. Then we're going to go in with the reamer. Going in with a reamer is going to make it very easy to hit the size tolerance. And since the reamer is going to follow the drilled hole that we just made, the final hole is also going to be very concentric to datum A. Now, before I forget, the reason that we're using a number 32 drill is because it's just a little bit smaller than this reamer. Of course, we have to leave a little bit of material for the reamer to remove, but we don't want it to be too much. It's usually like, I don't know, 6 to 15 thousandths of an inch or so. It depends a lot on the size of the reamer. This is a pretty small one. According to our handy-dandy drill chart, a number 32 drill has a diameter of 116 thousandths of an inch. So that's about 9 thousandths of an inch smaller than 1/8. When it comes to the 1/4 20 UNC 2B threaded hole, our strategy is going to be very similar. We don't have to be quite as careful because there's no perpendicularity callout, and that depth is actually not particularly difficult to achieve, as I'll talk about later on when we actually get to it. But it doesn't hurt to take similar precautions as we do for the pinholes. If we take another look at the drill chart, we'll see that for a 1/4 20 thread, the typical tap drill size is a number 7, which has a diameter of 201 thousandths. We've found that we have a little bit better luck passing the go, no-go test for pitch diameter size if we go one drill size smaller than that, a number 8, which has a diameter of 199 thousandths, only 2 thousandths smaller. So the sequence of operations is center drill, as always, number 8 stub drill, and then a 90-degree countersink so that we can create an entry chamfer on the hole. That just helps to get rid of incomplete threads at the mouth of the hole and helps to center the tap. And then finally, we go in with the 1/4 20 tap. This is a plug tap, which has a pretty aggressive lead chamfer on it in order to help the tap get started in the hole. This is really nice because it more evenly distributes the cutting forces, but we may not be able to get all the way down to the bottom of the hole to get our threads deep enough. So if we need to, we'll go in with a bottoming tap, which has a little bit less aggressive of a lead chamfer. This style of tap is something that we would use just to finish the threads close to the bottom of the hole. We'll use it if we need to. Okay, so there's the overall strategy for how we're going to make these holes in the top of the part. I'll talk more about these tools and operations at the machine, but hopefully this gives you enough of an overview so you won't be confused about what I'm doing and why. Okay, let's go ahead and take the part out. We're going to replace these thin parallels with these thicker parallels. I think these are inch and an eighth. Make sure everything's really nice and clean. Okay, parallels go in, part goes down. And actually, if you've got a really big burr on the backside of this hole that we just bored out, then you should kick that burr off with something like, I don't know, some kind of a deburring tool, just so that you're not sitting on top of this burr on the parallels, right? You want to be touching actual material right here. Okay, I've got 4 equal-sized shims, and one goes under each corner of the part, between the part and the parallels. Okay, I'm going to go ahead and tighten the vise. Good vise pressure. All right, tap this down. Let's check the shims. Oh, that one's loose. Tight, 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 and tight. Okay, good. Okay, the fancy drill chuck goes in next. Make sure that there are no chips in here, okay? We don't want to, basically we could destroy all of the precision and accuracy of this drill chuck by loading it up in there with chips in between the tapers. And actually it looks like somebody's already done that, so, there goes the tolerance that we paid for. Anyway, there we go. Okay, edge finder. Okay, so all of these hole positions are also given from this corner right here, the bottom left corner. So we need to find this edge and this edge. Okay, so that should be the corner right there. And it does look like it is. Don't forget to add half of the diameter of the edge finder, okay? So you have to account for that 100 thousandths. The first pinhole is 125 thousandths from datum C and 250 thousandths from datum D. Okay, go ahead and remove the edge finder. Okay, center drill goes in. Okay, 125 thousandths from datum C. Right there. All right, and then 250 thousandths from datum D, the front of the part. Right there. Now, I'm not going to zero this out, okay, because I need to find two other positions from that common zero, okay? So I'm just going to leave it where it is. Okay, turn this on, and then we're going to come and just sort of lightly touch right there. Okay, we don't need to make a big spot, just somewhere for our drill to locate. So that's plenty right there. And I'm just going to do a quick check to make sure that I'm, about 1/4 inch from the front and about 1/8 of an inch from the left side. Good. Remove this. Okay, the number 32 drill goes in. Right there. Okay, bring that down just to touch. So one question that we need to ask is, how deep are we going to go with this drill? The depth on the print is 500 thousandths of an inch, and that's 2 decimal places, so plus or minus 15 thousandths of an inch. But that is the depth of the full diameter of the hole, that 125 thousandths plus or minus 1 thousandths diameter. There's a little bit of extra depth that we need to account for the drill point angle itself. But actually, it's a little bit more complicated than just accounting for the drill point angle. The reamer also has a point on it. And this point is at a 45-degree angle as opposed to the stub drill's 135 degrees, and it's actually significantly longer. Just looking at it with a ruler, it's about 5/64 of an inch, or 78 thousandths. And we want to make sure that we can get this reamer deep enough into the hole so that we can get 125 thousandths diameter all the way down 500 thousandths of an inch. So if we go an extra 80 to 100 thousandths deep with the drill from where we are touched off right now on the top of the part, that should give us enough clearance to ream out that hole down 500 thousandths of an inch. This might change a little bit depending on how big of a spot you made, but it's a pretty good target. Okay, so this depth I'm going to base off of the quill readout, right there, okay? Zero that out. Okay, let's turn this on, adjust the speed. Okay, give it a little coolant. Okay. Okay, pull it out if you feel like it's getting bound up. Clear those chips. Okay, so we're just going to go to, say, 590, somewhere between 580 and 600. Perfect. Okay, let's go ahead and remove that little drill. Put in the reamer. Just like that. Now to position the reamer, I'm going to go ahead and bring this down just until the outside of the reamer looks like it is flush with the top of the part. Just like that, and then I'm going to zero that out. Okay, let's start that up. Okay, tap magic this time, just like that. Okay, and here we go. Now, if at any point you feel it start to bind, don't force it. There we are, 500 right there. Go ahead and pull it out. If you drilled the hole too shallow, and then you try to go in with the reamer and you can't get all the way to the bottom, obviously you're going to feel a hard physical stop. And if you try to force it past that point, you're probably going to break the reamer or at least cause it to cut really oversize. Okay, there we go. Okay, now we put the countersink in there. And with the countersink, all we're going to do is just kiss the top of the hole, making a tiny little broken edge. We don't want to put an actual countersink on there. Just kiss it. Right there. That's all you need. Perfect. Okay, now we just have to do the same thing for the other pinhole. This pinhole is supposed to be 812 thousandths from datum C and 1 inch 687 thousandths from datum D. Okay, countersink comes out, center drill goes in. 1 inch 687 thousandths in the Y direction from the front of the part. Right there. Okay, and 812 thousandths on the x-axis from the left side of the part. So right there. All right, start it up. It doesn't need to be much. Number 32 drill. Okay, go ahead and bottom that out on the top of the part there. Zero the z-axis. Start it up. All right, we'll go maybe 600 this time. Right around there. Remove the drill. In goes the reamer. Okay, bring that down just until the flutes on the reamer look like they're right at the top of the part. Zero that out. Okay, start it up. Tap magic. And we go 500 thousandths deep. Right there. Reamer comes out. Countersink. And then just kiss the top of the hole. All right, there we go. Okay, countersink comes out. Okay, center drill goes back in, and now it's time to do the 1/4-20 threaded hole. The 1/4-20 threaded hole is positioned 500 thousandths from datum C and 937 thousandths from datum D. So 937 thousandths on the y-axis, right there, and 500 thousandths on the x-axis, right there. Start it up. Come in and make a little spot with the center right there. Okay. Okay, number 8 drill goes in. Come and touch that off on the top of the part. Zero it on the z-axis on the digital readout. So the depth of the threaded hole is also 500 thousandths of an inch, but here it means the depth of the threads, okay? So a screw should be able to assemble 1/2 of an inch into the part. And even though this is a 2 decimal place dimension, it's actually not plus or minus 15 thousandths. It's supposed to be 500 thousandths plus or minus 15 according to the print, but according to the evaluation sheet that we get from NIMS, the National Institute for Metalworking Skills, who created this print and this project, it's actually listed as 500 thousandths minimum. So actually it can be much deeper than 500 thousandths. The only thing that they care about is that it's at least 500 thousandths and that you don't break through the other side of the part, the bottom of the part. That's all they care about. So the dimension from the bottom of this slot to the bottom of the part is 1 inch. So I'm going to go, let's say, 875 thousandths. Okay? That way I know I'm not going to break through, but I'll have plenty of room to finish those threads. Did we break through the other side? Nope. Good to know. Okay, now it's time for the countersink. With the countersink, all we're really trying to do is open up the mouth of that hole so it's the same size as the major diameter of the threads or just slightly bigger, so that we have a nice gradual entry to those threads. The major diameter of a 1/4-20 threaded hole is, of course, 1/4 of an inch, or 250 thousandths. I'm going to get the size of the countersink basically by guess and check. I'll be checking the size over the mouth of the hole with a dial caliper which I've set to 250 thousandths. So the jaws of the caliper are just slightly bigger than that countersink, so we could go just a little bit more. And that looks really perfect right there. It can actually be a little bit bigger than 250. Okay, we are done with the fancy drill chuck, so let me go ahead and remove it. So we're going to go in with this 1/4-20 tap. It has a plug style chamfer on it, meaning that it's about 3 to 5 incomplete threads. This is going to help us get the threads started. Okay? We're going to do this the way that you will be familiar from the drill press project, the NIMS bench block project. We're going to hold this in a tap wrench, and then we're going to put one of these spring-loaded tap guides into the spindle to help guide the tap wrench and the tap. Okay? This has a 1/2 inch shank which doesn't fit into the Albrecht drill chuck, okay? But it can fit into a collet. Okay, so that's how I'm going to hold it. Okay, make sure that you hold on to the square drive on the end of the tap. Screw that in tight. Let's see, we're going to need to make up a little bit of room there. Lower the knee. Right there. Some tap magic. Bring the quill down a little bit just to load that tap guide. Okay. I'm going to try and be really careful because these 1/4-20 taps are pretty fragile. Okay, so I'm going to wrench this back every now and then to break the chips, and be really, really, really careful if you feel it overloading. Once you're down to about this point, and you can see that you're past the chamfer on the tap, then you're going to want to start counting your revolutions. Not because you need to be some specific size, but just because you want to make sure that you can go at least a 1/2 inch down. And if this is a 20 TPI thread, that means so it's 20 threads per inch or 20 turns per inch. So for 500 thousandths, a 1/2 of an inch, we're talking 10 turns. So I'm just going to mark a position right here and use that as a reference. Okay, that's 1, 2, 3, 4, 5. Okay, halfway there. That's 6, 7. Okay, I need to bring the quill down a little bit. So that's 8. Be careful if you feel it start to bind. It may be because you're bottoming out on the bottom of the hole, or maybe there are some chips at the bottom of the hole, which is like the same thing as bottoming out on hard material. So you really want to watch out there, because if the tap doesn't want to go anymore and you force it, right, you can over torque it and then the tap will just snap clean in half. So that's 9 right there. Yeah, so we're bottoming out already, okay? So I didn't quite make it to 10 turns, but that's okay. Let me go ahead and back this out. Now I can go in with the bottoming tap, which has a much shorter chamfer on the end of the tap, and so I can make full threads much closer to the bottom of the hole. So at least 10 turns with this thing. Good idea to blow out that hole. More tap magic. Okay, get this thing started in the threads. Okay, I'll mark it off. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so actually we did go 10. Okay, so that's actually 11 right there. Okay, so we went actually maybe closer to 11, 11 and a half. Okay, that's all we need. Yeah, I mean, it's 500 thousandths minimum, right? So it's not a very tight tolerance. You can kind of just go deep enough. And if you need to go closer to the bottom of the hole, you can use this bottoming tap. If you don't need to, then don't. Okay, folks. We're basically done with this part now. There's just one thing left to do. I know there's always one thing left to do, but this really is the last thing. We need to put a countersink on the back side of this hole. So let me take this out of the vise, flip it around, and put the big countersink back in the spindle, and then I'll show you how I do it. So all I've done is flipped the part over, and so now the tops of those 2 tabs are sitting down on the parallels. The trick here is that we need to re-find the center of this bore. And you might think, well, you could just go in with the edge finder and touch off the two surfaces that we touched before and go over the same distance, right? And then we would be able to refine the hole. And that would work to a certain extent, but it's not the most precise way to find the center of a hole. The most precise way is actually to use an indicator. It turns out that finding the center of a hole, or any kind of cylindrical object on a milling machine with an indicator, is actually a very, very common machine shop task. So this is a good opportunity for you to practice a little bit. So let me go ahead and install this. Okay, what I'm going to do is position the indicator like that, and I'm going to adjust the position of the indicator body so that it, oh, see, now it's not sweeping really any circle at all. I want it to be sweeping a circle equal to the size of the diameter that I'm trying to measure. So let me just adjust until it's doing about that. Okay, now using this, we can kind of roughly align the hole, just left and right using the XY axes on the table, okay, something like that. So now it looks like, if I just bring this a little bit closer, okay, so it looks like we're pretty center here, but it also looks like we're a little bit too big with the circle that we're inscribing with that pointer. Okay, so I'm actually just going to bend that in a little bit just so that we can get inside of the bore. Okay, now I'm going to try and sweep that hole in. Okay, you can see that the indicator moves around as I turn the spindle. Okay, so this is just like indicating a 4-jaw chuck on the lathe. Okay, I can adjust it in this direction and in this direction, and I want it to read 0 in this direction, meaning that the indicator comes back to the same position here and here, and I want it to come back to the same position here and here. So we're looking for opposing points. Let me go ahead and 0 it right here. Now if I start going in this direction, you can see that it's going counterclockwise, which means that the hole is a little bit this way. And you can't really see what it says on the back side, but it actually goes even more in the counterclockwise direction, about 20 thousandths or so. Okay? So I'm going to move this half of that, 10 thousandths, in the counterclockwise direction, and then I'm going to try to re-zero it. Oh, it's pretty stiff. Okay, right there. Let's see what it is on the other side. And it's about minus 10 thousandths. Okay, so let's go another 5 in the counterclockwise direction. I am going to have to re-zero that. It's a little bit finicky to adjust the 0 on this. There are actually some special indicator holders that are made for, they have a fine adjustment on them so that it's easier to set a 0. That's good enough. 0. And just a little bit under 0 over here. Okay, so let's go ahead and do the left to right. So this is saying -7. So let's move it to the 0. Okay, now let's check the other side. Oh, and that's a pretty good sign. It's not moving very much when I spin it. On this side, it's saying -3. -3. Okay, and so I'm going to go -1.5 on this side. And then re-zero it. 0. And just about 0 over there. What is it over here? Let's see. 0. -0.5. Okay, let's go back over here. So this says 0 and -1. Okay, so let me go -0.5. So 0, minus a half, 0, minus a half. So that's basically 0 everywhere within a half of a thousandth of an inch. Basically, if you're on center of the hole with X and Y, then you should be able to put the indicator in there, put it on the inside surface, sweep it around, and it should read the same thing everywhere, meaning the pointer arm shouldn't move. And if it does move, then you just adjust it left and right and forward and backward using the X and the Y axis until it does read 0 everywhere. Very effective. Okay, and then the way that we actually make the countersink is the same way that we made it on the other side. So let me bring this in a little bit closer. Lock the quill, turn it on, adjust the speed. Slowly raise the knee till we just touch off. There's a little bit of a burr on there, so I'm going to go a little bit deeper. There. That's a real touch off. Okay? I'm going to go ahead and zero out the dial on the knee. Give it a little tap magic. And then 30 thousandths. And that's all it takes. Well, there you have it, folks. That is the NIMS Step Block from beginning to end. I won't lie, this is a pretty ambitious project for a relatively new machinist, but there are so many different things, very important points to learn along the way, that I think it's really worth going through the process. We still need to go in and do a final inspection of this part. And the inspection for this part is actually just as interesting as the making of the part. But that's going to be another video. So for now, thanks for watching, and I'll see you later.